This is a $2 billion B-2 Spirit, the most complex flying machine ever created by human engineering. But keeping this radar-evading ghost in the sky requires a factory-level precision process where missing a tolerance by even a fraction of a millimeter turns it into the world's most expensive paperweight. Inside climate-controlled subterranean facilities, high-precision automated assembly lines and specialized chemical laboratories work around the clock to craft, coat, and weaponize this stealth titan. The manufacturing journey begins inside an ultra-clean assembly bay. The air temperature here is locked at exactly 68 degrees Fahrenheit, preventing microscopic thermal expansion in the laser gyroscopes. Technicians align the MAU-169 laser guidance assembly to the weapon chassis. Inside sits a specialized GPS antenna no larger than a hockey puck, flanked by inertial sensors capable of measuring microvibrations thinner than a human hair. Next comes the high-speed data umbilical interface, a gold-plated connector that acts as the direct communication bridge between the aircraft's central mission computer and the weapon's guidance brain. Using calibrated digital torque wrenches, technicians secure the casing bolts. Over-torquing cracks the composite housing, while under-torquing allows supersonic acoustic vibrations to destroy internal circuitry. Robotic tail kit actuators are bolted on. Each control fin is powered by independent high-torque electric motors, capable of adjusting pitch and yaw in increments of 1/10 of a degree. Automated test rigs flex the control surfaces through full 360-degree cycles. If a fin binds for even half a second, the entire guidance kit is scrapped. Precision load cells weigh the complete assembly down to the gram. The bomber's ballistic flight computer demands exact weight metrics to calculate high-altitude trajectory physics. Until release, the weapon remains completely inert. Its thermal battery remains uncharged until subjected to extreme pneumatic ejection G-forces. Once certified, the munitions are sealed inside climate-controlled transport capsules, protecting sensitive ring laser gyros from tarmac temperature spikes. While weapons are prepped in clean rooms, the stealth bomber itself undergoes electromagnetic surface conditioning out on the flight line. Stealth performance isn't magic, it is an aggressive manipulation of electromagnetic energy requiring flawless microscopic surface geometry. The bomber's skin is bonded with radar-absorbent material containing microscopic iron spheres that vibrate when struck by radar waves, instantly converting incoming energy into harmless heat. However, RAM coating is extremely fragile. Rain, hail, or supersonic friction can create microscopic scratches that bounce radar signals straight back to tracking stations. Technicians inspect every square inch using optical micrometers, paying special attention to leading wing edges where incoming radar waves hit first. Panel seams are sealed with conductive silver-infused tape. A surface gap no wider than a credit card is enough to spike the aircraft's radar cross-section exponentially. When surface flaws are detected, technicians use pneumatic sanders to remove damaged layers without digging into the underlying carbon fiber structure. Specialists mix synthetic radar-absorbing compounds with strict pot-life timers. Apply it too fast, and air pockets form. Apply it too slowly, and it refuses to bond. Infrared heating lamps cure the polymer patch at precise thermal thresholds, preventing microscopic bubbling. Once cured, technicians hand sand the patch using ultrafine abrasives, removing material in increments measured in thousandths of an inch. The finished skin cannot vary by more than the thickness of a paper sheet across any 12-inch span. You aren't just repairing an aircraft, you are sculpting an electromagnetic shield. Simultaneously, mechanical crews test the quad-redundant hydraulic system, which pressurizes fluid to over 4,000 psi. Dual-stage flight control actuators undergo high-frequency response testing to verify zero lag in tailless flight control responses. Heavy-duty titanium landing gear struts, carbon composite brakes, and high-pressure tires pass rigorous stress inspections. With low observable skin and mechanical systems certified, hydraulic lifts roll the precision weapons underneath the bomber's internal bay. Unlike conventional aircraft, every single weapon must fit inside the airframe to preserve the aircraft's stealth geometry. Massive internal bay doors open, exposing the core rotary launcher, a massive revolver-style drum capable of holding 8 2,000-pound munitions. The heavy drum rotates 360 degrees in under 3 seconds, moving 8 tons of precision equipment with extreme hydraulic smoothness. Heavy suspension hooks rated for 14,000 pounds of force clamp onto the weapon lugs, locking the weapons in place against high-G combat maneuvers. Once locked into the rotary hooks, digital umbilical cables plug directly into the aircraft's central stores management system, enabling real-time targeting updates. Targeting coordinates stay locked inside the bomber's encrypted core computer, loaded into the bomb's guidance brain just seconds before release. In parallel, life support specialists inspect pressure helmets integrated with heads-up displays, night vision optics, and thermal flash protective visors. Anti-G flight suits undergo pressure chamber calibration to prevent pilot blackouts during heavy combat banking maneuvers. Ground crews then begin hot pit refueling, a high-risk operation where fuel is pumped while all 4 turbofan engines remain running at idle. Refueling specialists wear aluminized thermal proximity suits to handle high-flow fuel lines near exhaust blasts exceeding 1,000 degrees Fahrenheit. Heavy copper grounding straps clamp onto the landing gear, safely discharging thousands of volts of static electricity built up during flight. High-pressure hoses pump 167,000 pounds of specialized JP-8 jet fuel at a staggering rate of 600 gallons per minute. Because a flying wing airframe has no tail fin, automated fuel management computers dynamically balance weight across internal fuel cells. Fueled, armed, and stealth certified, the flight crew climbs the ventral ladder into the glass cockpit flight deck. Pilots secure themselves into rocket-assisted ejection seats engineered to clear the airframe in under 1 second, even at 0 altitude. Dual-ring laser inertial navigation units undergo an 8-minute alignment phase, measuring the Earth's precise rotation vector. During taxi, pilots actuate the wingtip split drag rudders, the primary mechanical surfaces used to control directional yaw on a tailless aircraft. Multiple sensors verify elevon travel, ensuring digital flight computers can execute microcorrections 1,000 times per second. For turbofan spool up to full military power, generating nearly 70,000 pounds of thrust to propel the 336,000-pound bomber down the runway. Cruising at high altitudes, quadruple flight control computers execute continuous surface microadjustments to keep the inherently unstable flying wing perfectly level. As the aircraft approaches target coordinates, the internal rotary launcher rotates the selected weapon into the bottom release slot. The massive weapons bay doors snap open for only a fraction of a second to prevent exposing internal radar reflections to ground radars. Through the data umbilical, the mission computer uploads final GPS coordinates, wind vectors, and barometric data into the weapon in milliseconds. High-pressure pneumatic ejectors fire, forcing the weapon clean out of the bay at 4 feet per second. The moment the umbilical detaches, a thermal battery ignites, powering the internal guidance brain and unlocking the motorized tail fins. The guidance computer calculates an optimal flight trajectory, dynamically flexing the tail fins to trade altitude for horizontal range. If GPS signals are jammed, internal optical and inertial sensors take over navigation instantly, holding precision paths without external signals. In the final terminal descent phase, fin actuators adjust hundreds of times per second to neutralize high-altitude crosswinds. Integrated radar altimeters trigger the precision impact fuse at the exact target coordinate elevation. From cleanroom sensor assembly to microwave-absorbing skin sculpts, every single component represents the pinnacle of modern automated engineering. The end result is an unrivaled masterclass in aerospace manufacturing, a $2 billion engineering marvel built to dominate the skies. As the bomber lands safely back at base, automated inspection systems immediately begin scanning its radar-absorbent skin for the next mission cycle. Because maintaining total air dominance requires an endless cycle of extreme manufacturing precision, automated testing, and obsessive quality control. And it all starts right back here, inside the world's most advanced stealth bomber factory.